You feel completely fine, but your doctor suggests a routine screening just to be safe. A week later, the phone rings. Imagine a test for a serious disease. It's 99% accurate, you take it. The result comes back positive. How worried should you be? Most people, including many doctors, would say 99%, almost cert. But the real answer can be astonishingly different. For the disease we'll use, your actual chance of being sick is only about 9%. You are far more likely to be perfectly healthy. A 99% accurate test, a positive result, and you're probably fine. How can that be? The answer is one of the most important and most misunderstood ideas in all of probability, Bayes' theorem. Let's set the scene carefully because every number matters. First, the disease. It's rare. It affects just one person in 1,000. Now the test. When we say 99% accurate, that's really two promises. If you are sick, it catches it 99 times out of 100. And if you are healthy, it correctly clears you 99 times out of 100. That sounds excellent. Only a 1% error rate either way. So surely a positive result means you're almost certainly sick. Let's see why that intuition falls apart. Keep both numbers in your head, 1 in 1,000 and 99%. The whole puzzle lives in the tension between them. Here's the trap your brain falls into. You hear 99% accurate, you get a positive, and you map one onto the other. Positive must mean 99% sick. But the test's accuracy and your chance of being sick are not the same question. The test doesn't know how rare the disease is. You do, and that rarity changes everything. So let's not argue with intuition. Let's count. Forget percentages for a moment and picture 10,000 real people all taking this test. First, how many are actually sick? The disease hits 1 in 1,000. So out of 10,000 people, just 10 are truly sick. The other 9,990 are healthy. Now run the test on the 10 sick people. It catches 99% of them, so essentially all 10 get a correct positive. So far, so good. But here's the part everyone forgets. Run the test on the 9,990 healthy people. It's right 99% of the time, but wrong 1% of the time. 1% of nearly 10,000 is about 100. 100 perfectly healthy people get a positive result anyway. False alarms. Now line up everyone who got a positive. 10 of them are truly sick. About 100 are healthy, but falsely flagged. That's 110 positives, and only 10 are real. So if your test is positive, your chance of actually being sick is 10 out of 110. That's about 9%. The false alarms simply drown out the real cases. Stop and feel how strange that is. The test almost never lies, and yet when it speaks, it's usually wrong. Not because the test is flawed, but because the disease is so rare. Before we go on, sit with this for a second. What if the disease were more common? Say 1 in 100 instead of 1 in 1,000. Pause and predict. Does your chance of being truly sick go up or down? Think about how many real cases there would be versus the false alarms. It goes up a lot. Let's actually count it. With 1 in 100, there are now 100 sick people in our 10,000, and the test catches them all. But the false alarms barely change. Still about 100 healthy people wrongly flagged. 200 positives now, and half of them are real. 50-50 from the exact same test. The only thing we changed was the prior. What we just did by hand is Bayes' theorem. Let's name the pieces. Your starting belief, how likely you were to be sick before the test, is called the prior. Here, 1 in 1,000. The test result is the evidence. Bayes' theorem tells you how to update your prior in light of that evidence to get the posterior, your belief after the test. In words, the chance of being sick given a positive equals the chance of a positive given sick times the prior divided by the overall chance of any positive. Plug in our numbers, and out falls the same 9%. So one number, how common the disease is, silently controls the entire answer. Ignore that prior, and you can be wrong by a factor of 10. The deep lesson hides in that little prior. Evidence doesn't replace your starting belief, it nudges it. A positive test multiplied the odds of being sick by 99. But those odds started from almost nothing, so 99 times almost nothing is still almost nothing. Watch what happens as we slide the disease from common to rare. Common and a positive is alarming. Rare and the very same positive barely moves the needle. The prior is doing the heavy lifting. And this isn't just about medicine. The same trap appears everywhere we weigh evidence. A spam filter flagging a rare important email, a face recognition match in a crowd of millions, a courtroom statistic that sounds damning but ignores how rare the crime is. Lawyers call it the prosecutor's fallacy. In each case, ignoring the prior turns strong-sounding evidence into a misleading one. Bayes is the cure. Always ask, how likely was this before I saw the evidence? Because that's what thinking clearly really is. Not certainty from a single test, but a belief, updated honestly, one piece of evidence at a time.